Hello, this is Stuart Mason for Math 156 with script 3B. We're going to be doing some more permutation testings, but this time we're going to be dealing with a data set that is highly skewed and also has highly uneven sample sizes. The point of this is to illustrate how much more robust permutation tests are relative to more classical hypothesis tests. So for example, if we wanted to compare the means of two different samples as with a t-test, we really need the underlying populations to be distributed normally, unlike with the permutation test where we don't need that assumption, as we'll see in this example. So we're going to be using the Verizon case study, so go ahead and set your working directory appropriately, grab the verizon.csv data from the textbook website, and let's read it into memory. So what this data set has is just two columns, the amount of time in hours it took for a problem to be repaired, and whether the problem was suffered by a customer of the incumbent local exchange carrier or CLEC, the competing local exchange carrier. Basically, Verizon is the ILEC for a large portion of the eastern United States, and so because they have this large swath, it's their responsibility to handle problems for smaller competing carriers, the CLECs, in that region, and they're subject to fines if they substantially favor their own customers. And so what we're going to ask of this data set is, do they seem to be favoring their own customers, or is everyone being treated fairly? So let's store this time column in its own vector for called time in case we need it later. And we're also going to create a list of the two vectors using our split function. So we're splitting the time column based on the group column. So run time split, and let's just take a look at the output. So the result is this very long list of vectors. So let's go to the head here. You see you have the first list item, CLEC, is a vector that's just a few elements long, and the second is the ILEC list item, and it's a much, much longer vector. But this whole object, this whole variable, is just a list of vectors. I don't know if we've seen lists before, so I'll quickly talk about them. Much like vectors, you can access the elements numerically, except that instead of one open bracket, we use two open brackets. So if I go double open bracket 1, we'll get the first element, 2 will give us the second element. Also, just like in a data frame where you can access the columns using the $ operator, you can access list elements using the $ operator. And that's what Paul's doing here when he calls mean on each of the elements. So we can take the mean of ILEC and the mean of CLEC, and that shows us that it happens that the mean of the Verizon data is much less than the mean of the CLEC data, and we'll use a permutation test shortly to see if that difference means anything. Sort of to illustrate another function here, we're going to use lapply, this is list apply, to apply the length function to all of the list items in the time split list. Basically, we'll be taking the length of both vectors in time split, and you see one is 23 items long, one is 1,664 elements long. So now let's compute our test statistic, which is the difference in sample means. It's just about 8. And we wonder if this is significant. So let's try to get a feel for the population here. We'll take the histogram of time, and you see it's very, very non-normal, although it does have this kind of bell-shaped-ish behavior here in the middle, but most of the repairs take just about under an hour. There is this very long tail of repairs that take, looks like multiple days. And so Paul points out that we can see that there's plenty of skewness, but let's compute the skewness statistic just to practice doing it, and you see it's 4.52238. Paul says comparing it to 1 is meaningful, so it's sort of much more than 1, it's positive, so that means we have a right. Now we're going to do a permutation test. It's exactly the same as before. The only difference is we don't have even sample sizes. That's it. So our index is going to be a sample of the entirety of the length vector, but only as many as there are elements of CLEC, so that's just going to be 23. And you see index is 23 random rows spanning the entirety of the length vector. We can compute sort of a permutation statistic, and we'll initialize our n variable to say how many times we're going to do this, and we'll run this process just about 100,000 times, storing each result in a vector, and we'll see what the distribution of these statistics looks like. Okay, so it's a nice histogram, has a little bit of a skew, and this is part of the point. Our test statistic need not be distributed normally for us to use a permutation test, so we can press on. So as always, we're going to draw an AB line of where our actually observed statistic lies, and we'll use this logical sum to figure out how rare that is. And you see it's significant at the 5% level, not quite significant at the 1% level. And just like before, we don't have to use the mean, we can use other statistics. So here's the difference in sample medians. The medians are nice because they're more robust than means. They're not as affected by this tendency for the data to be very, very large. The textbook puts it another way and points out that the mean sort of treats 10 additional hours after 1 hour the same as 10 additional hours after 100 hours. But in the context of waiting for repairs, that's a big difference. And the median will be not affected by that, or the median is not insensitive to that change in scale. So let's perform the same permutation test, but with a difference in medians. Look at the resulting histogram. And you see that it's less skewed because it's less likely that basically you'll have very long repair times messing up the medians, and that it's sort of very, very rare that in your small population of 23 you're going to get enough large values to throw off the median. And throw in the AB line, take the p-value. You see it's smaller because it takes a less convincing shift, or it takes a less extreme shift to confuse the median. Now, this is a good time to point out that it's not really fair to run a bunch of different tests on the same data until you finally get the result you want. Really, you should design the test as best you can once, run it once, and then you get the result. And if you want to run more tests, you have to get more data. Because otherwise, think about it, right? What you're testing for is the ability for the data to randomly fluctuate a certain way, assuming that the effect isn't present. If you make that assumption over and over again, and you run these tests over and over again, eventually you're going to get a result that seems significant, even though it's happening just by random chance. Right? If you're testing at the 5% significant level, then one test out of 20 will say, yes, there's an effect, even if there isn't one. However, for the purpose of looking at different possible statistics, we're going to press on and keep slicing up this data different ways. So here Paul uses the ratio of means as the test statistic. So basically, is this very, very different from 1 is the question. And same exact idea, right? We sample. We take the ratio of the mean with just the sample, divide that by the ratio of the mean without the sample, and store that in a vector. Plot all the results, draw where r's occurred, and calculate how much of the mass lies to the right. This one's a bit different. We're going to be considering the proportion of repair times greater than 10 hours. So again, it's just the mean of a logical vector gives you a proportion, and we're asking how many of the hours are bigger than 10 in each case. And as Paul points out, well, we only have 23 samples in the CLEC vector, so maybe this big difference is because of, you just got unlucky with the presence of high wait times, but a permutation test will show that it's unlikely that you'd get this unlucky. So what's the overall proportion? About 23, and this should be unsurprising because remember, most of the data is ILEC, the ILEC proportion is about 23, so it makes sense that the total proportion is about 23. And so given 23% of the time you expect this to happen, how many do we expect to get in a data set of 23? And the answer is between 5 and 6, but we observed 13. So probably too many, let's find out. So what we're going to be using as a test statistic here is the difference in those proportions. So proportion of CLEC over 10 minus proportion of ILEC over 10, and we'll permutation test that statistic. Histogram the results, add the AB line, and you see again, very, very rare to see this. Although keep in mind, we did cut the data up a lot of different ways, but since they all yielded the same result, it's pretty convincing that there's something going on here. Although before you rush to drop Verizon as your character due to their crooked business practices, I would point out that the textbook mentions that they actually conduct many, many thousand such tests and see if a greater than 1% proportion of them show significance at the 1% level. So it could be that the authors just picked a data set that happens to show this result for the sake of giving us an interesting data set to work with. So I'm not really sure if Verizon is up to no good or not. But anyways, that's it for script 3b. So thanks again, and I hope this was helpful. As always, send your questions to smason@post.harvard.edu, and I'll see you guys on Wednesday.